So today's speaker for seminar is Leia Otterstatter. She started as an undergraduate researcher in my group, 2021, 22.
Yeah, 20,
something like that.
Yeah, junior year.
Stayed on to do a master's degree with me, and today she'll be talking to us about her master's research, which focuses on analysis of some of the data from the armed Southern Great Plains site. So without further ado, I'll turn it over to you.
Well, thank you all for coming today, and thank you for everyone online for coming and showing up and supporting me through this. So yes, as Scott said, my name is Leia Otterstatter, and I am a second-year master's student at the University of Oklahoma. And my presentation is Heat and Moisture Transport Dynamics within the Convective Boundary Layer, Insights from the Southern Great Plains ARM site. So to start at the very beginning, I understand that while this is a boundary layer seminar, maybe not everyone who is in here quite understands the boundary layer. So what exactly is the boundary layer? There is several definitions of what the boundary layer is, but it is the lowest 1 to 2 kilometers of the atmosphere, directly influenced by surface forcing with a response time of about 1 hour or less. And it is a region of strong exchange of heat, moisture, and momentum with the surface. So there are 2 main stages of the atmospheric boundary layer. There is the convective boundary layer, also known as the CBL, and the stable boundary layer, also known as the SBL. So with the CBL, you have unstable temperature stratification, and it occurs during the daytime and is a lot deeper than what you see during the nighttime, which is where you get the SBL, which has stable temperature stratification, which again occurs at nighttime, is shallower, and stable stratification essentially means that buoyancy is smushed down, so it's more horizontal than it is vertical. So this, if anyone who has done boundary layer research has probably seen this time and time again. This is based off of a Stull diagram, and it shows on the x-axis, it is time throughout the day, and the y-axis is height. So what we are focusing on is the green part that you see, the convective mixed layer, or the convective boundary layer. So the CBL forms daily from surface heating, and that is caused by turbulent mixing with cooler air aloft. And then that mixing leads to the formation of the entrainment zone, which you can see on that side as the convective boundary layer continues to develop. And that's the region where the free atmosphere air is entrained into the mixed layer and thermals overshoot upward. So turbulent mixing in the ABL drives the exchange of heat, moisture, and momentum, which impacts weather and climate patterns that we see. So this is the idealized version. So now let's take a look at what it actually looks like. This is one of my cases from my project. This is vertical velocity time height plot for August 1st, 2018. So as you can see again, on the x-axis is time, and it goes from 0Z, which is 7 p.m. to 7 p.m. of the following day. So this shows, August 1st. And then on the y-axis is with height. So I've annotated this. So starting at 0 UTC, or 7 p.m. Central Time, you can see the collapse of the CBL from the previous day. And then the stable boundary layer begins to form after that. When sunset hits, it collapses within a matter of minutes. And then a couple hours after sunrise, and I've labeled that in red, the CBL forms and evolves throughout the day. And so once the sun comes out and begins to heat the surface, you have that the thermal plumes begin to rise, and then the convective boundary layer begins to form. So the darker the color that you see within CBL is the stronger the vertical velocity. So red is an updraft and blue is a downdraft. So this is what it looks like for one particular case in general. So why is this even important to begin with? Why do we study the boundary layer? So it turns out that everything that we experience at the surface occurs within the boundary layer. Unless you are in a plane or taking off in a Blue Origin rocket ship for 11 minutes, you are experiencing what's going on within the boundary layer. So any forecast that you have for wind, temperature, frost, humidity, those are all boundary layer forecasts because we are experiencing them here. And they also control key processes of cloud formation, storm development, and pollutant dispersion. And it influences weather, climate, and air quality near the surface where we live. And it is also essential for improving weather forecasting and climate models. So now getting into our project focus here. So in order to better understand real-world variability of the convective boundary layer, this project investigates heat and moisture transport structures within the CBL under different stability regimes using Doppler and Raman LiDAR, as well as surface flux measurements that are collected at the Southern Great Plains ARM site. And I'll get into that site in a little bit. But in order to do that, we analyzed high-resolution data from the Southern Great Plains site, and we are specifically looking at the summer of 2018. So that is May 15th through October 15th, 2018. And we are examining different ABL conditions and how they impact the convective boundary layer structure and evolution throughout that time period. And we also want to identify humidity boundary conditions and how they influence transport within the CBL. So our research questions that we are investigating, the first is, how do humidity field properties impact mean profiles of turbulent statistics within the CBL? And second, do large-scale motions in the CBL exhibit similar spectral properties for temperature as well as humidity? So taking a look deeper into the Southern Great Plains ARM site, it was established in 1992, and its location goes anywhere right in this region from north central Oklahoma and southern Kansas. So each marker shows a measurement location where observations are taken. That entire area is around 9,000 square miles. However, the central facility where I get all of my data from is 160 acres in Lamont, Oklahoma. And you can see that with the red star that is up there. So continuing on, the key features of the ARM site. So it is the world's premier ground-based observations facility, and it has over 50 instrument platforms. And they range from radiometers to radar to LiDAR. You've got surface meteorological measurements, aerosol cloud measurements, as well as radiosondes, also known as weather balloons. They were launching those 4 times a day. However, due to the helium shortage, they've gone down to twice a day at 0 and 12 UTC, which can also cause issues when studying the boundary layer. As you know, 7 a.m. and 7 p.m. is at the start of the boundary layer growth, and after or right at the collapse. So we're missing a lot of what's going on there. So continuing on, just so if you ever wanted to look at data within the ARM site, so it's very accessible. They provide continuous high quality atmospheric data, and all data that is gathered is transmitted to the ARM data center. So it's not just the Southern Great Plains site. There are sites all over the world where you can get that data from. And it is freely available to the scientific community, and it is at the ARM data discovery site, which you can see in the picture on the right. So getting into our data and methods. This is our instrumentation. This table here shows all 6 instruments that we use. So it ranges from Doppler LiDAR to value-added products from Doppler LiDAR, surface measurements, Raman LiDAR, as well as algorithms to find what we're looking for. And I will get into that in a little bit. But this has the ARM name, the data name, as well as the temporal resolution and the spatial resolution. So getting into the total sky imager first, quick overview. So it is a rotating heated hemispheric mirror. That is the image of it, and it's annotated with each piece. And the shadow band blocks direct sunlight. So the charge coupled device, also known as the CCD camera, captures sky images every 30 seconds. And essentially what it does is once it captures that, it masks any obstructions from the camera arm, and classifies each pixel as either clear sky, thin clouds, or opaque clouds. And then it gives you that ratio or percentage of the sky cover that you're looking at. And the output, which is what I use for my research, so it calculates and stores the sky condition fraction data, and then from there I'm able to choose what percentage I want to look at and examine. So next, taking a look at Doppler LiDAR. So this is an active remote sensor, and it measures radial velocity, as well as backscatter and signal to noise ratio. And the temporal resolution is every 3 seconds. Spatial resolution is every 30 meters, so you'll have a data point every 30 meters within the boundary layer. And it is pointed vertically to retrieve height and time resolved vertical velocity data. And that is also an image of what the instrument looks like there. So from that, there's a Doppler LiDAR wind value added product, or VAP, and the purpose of this is to capture high resolution horizontal wind measurements. So this is one of my cases from May 18th, 2018. And as you can see, this is for one case, also 1 hour is one case. So from 15 to 16 Z. And each cross section of that throughout the hour at that location or height is the average wind speed, or U bar. So it is able to, I was able to calculate U bar at a constant height over the course of 1 hour. And this is because I needed a single value for wind speed over the course of one case for calculations that are made within this project. So taking a look at the Raman LiDAR, the general overview is that it is a semi-automatic ground-based laser remote sensing instrument, and it provides both height and time-resolved measurements for water vapor mixing ratio, which is a big key part of this project, considering that we're looking at moisture. You've got temperature as well as aerosol backscatter. And this can range from approximately 200 meters to above 10 kilometers above ground level. Granted, as stated earlier, the boundary layer only goes up 1 to 2 kilometers, so we're not going to use all of that, but it is helpful when we want to examine the boundary layer through there. And so the temporal resolution is every 10 seconds, and the spatial resolution is every 60 meters. So it's a little lower resolution than the Doppler LiDAR, but it is still high resolution. Taking a look at eddy correlation flux, also known as E-core data. So this instrument measures fluctuations in vertical wind velocity as well as scalar quantities at the surface. And it is widely used in studies for energy balance, carbon and water cycles, and what I am using it for boundary layer dynamics and turbulence. And continuing on, in order to find the atmospheric boundary layer height, we originally were planning on using ceilometer data. However, we ran into an issue where it provided 3 different heights at which the boundary layer could possibly be. And that's a problem when you want to make sure that you are getting the correct height for calculations within an hour. So I decided to use the Sawyer-Lee method, and that was used to obtain ABL depth, or ZI, measurements. And using the Sawyer-Lee method, it is derived from micropulse LiDAR data, and it estimates the height of ZI. So this is one of my cases, and this is for an entire day. So the blue is ZI, so how the boundary layer depth is changing throughout the day. And since since one case is equal to 1 hour, I found the average height for each hour. Hello? There we go. Okay. And that is in a red, that's a red dot that you see there. Oh. Sorry, give me 1 second. We're having technical difficulties. Okay. So moving on to our methodology. So again, our time frame is from May 15th through October 15th, 2018, which encompasses all of those days that you see in red here. So it was 153 days within the time frame that we're looking at, and that is 3,672 hours or cases. However, we want to make sure that these are all fitting the parameters that we are setting for ourselves for this project. So we started with cloud cover and radiation. So using that total sky imager, we wanted to look at daytime hours only, since the convective boundary layer occurs during the daytime. And we also selected 5% or less for cloud cover, because we wanted to make sure that they were clear sunny days to see what was going on. And then from there, looking at Obakov length, also known as L, we wanted unstable cases, because that's what you should see within the convective boundary layer. And so when they are less than 1 or negative, that means that they are unstable. And so those were selected. Next, we look at the boundary layer depth. And if anyone has worked with observation data, you know that sometimes not all the data is there and there are missing values. And that is a challenge that we hit here. And so we had to exclude data with missing ZI values. And then continuing on, looking at the convective velocity scale, we excluded cases with negative W star values, as we want ones that are positive, because that is what makes sense. And then for Raman LiDAR, that also had missing data. And so we excluded hours with that. So with all that being said and done, we ended up with approximately 15 days, which turned out to be 107 hours or cases that we're looking at. So now getting into results. So on the left, you can see that there's a distribution of case instabilities for the global stability parameter. And this is negative ZI over L. So the closer you are to 0, the more neutral it is. However, it can increase, towards infinity, and that as it increases towards infinity, that is highly convective. On the right, you see Obakov length, which is a measure of atmospheric stability, all for the same cases, all 107 of them. And L is negative, which indicates unstable conditions with strong convection occurring near the surface. So when it's closer to 0, that means that it is highly unstable. And when it is going towards negative infinity, it's still unstable, but it is less unstable. So therefore, that is going to be weakly unstable. Now, taking a look at this, this is pretty much the same plots that you saw. However, this is now a distribution of cases for global stability and Obakov length with instability regimes in place. So there were hourly stability cutoffs using global stability that follow Salesky and Anderson 2018. And each regime, so from highly, moderate, and weakly unstable, they correspond to systematic differences within the convective boundary layer structure. So weakly unstable, there's increasing shear relative to buoyancy, and you will get convective rolls. And as you increase instability, you will see more cellular convection. So there are different types of instabilities or cases that we're looking at. So you can see the distribution there, and then looking at the Obakov length, you can see that for highly unstable, we have 58 cases. Moderate, there's 36. And weakly, there's 13 cases. So again, that equals 107 cases there. So now taking a look at Bowen ratio and evaporative fraction. So Bowen ratio is the ratio of sensible to latent heat flux, and it goes from 0 to infinity within the convective boundary layer. Now taking a look at evaporative fraction, this is latent over sensible plus latent heat flux. So we use this because it is more constrained. Instead of going from 0 to infinity, it goes from 0 to 1. So you are able to visualize and see the data a lot clearer. And as it is closer to 0, sensible heat dominates. And as you get closer to 1, latent heat begins to dominate over here. And we'll get into that more later. So taking a look at this, this is a joint PDF of global stability and evaporative fraction. So you have global stability on the x-axis and evaporative fraction on the y-axis. And you can see, I know this might be a little complicated to look at. Trust me, it took me some time to fully understand this as well. But if you follow the arrows here from the peaks that you see from the histograms, you can then see hotspots that are occurring here. So looking at the higher evaporative fraction is associated with weaker instability. So that's usually when you have a moist surface, you have increased latent heat flux, and then from here, this suppresses buoyancy-driven turbulence. When you have lower evaporative fraction, that's associated with higher instability with what we see. And that's when you have a drier surface, there's increased sensible heat flux, and that enhances buoyancy production. So overall, big picture correlation between global stability and evaporative fraction is negative. There's a negative correlation coefficient of negative 0.227 that you can see here. And then continuing on, these plots show how moisture and temperature fluxes vary with instability. So in the left panel, individual profiles are grouped by instability regimes for the highly, moderate, and weakly convective, or yes, unstable. And under the unstable conditions, the fluxes are stronger, and the weakly unstable cases, they are weaker. And the right panel shows the composite mean, which is that solid line that you see of all these cases or spaghetti plots. So you can get more of a visualization of what is occurring with the fluxes. And there are standard deviations spread for each regime. So the darker shaded region is 1 standard deviation, and then the lighter is 2 standard deviations away. So continuing on, here we show the vertical velocity variance and temperature humidity covariance. And the vertical velocity variance peaks around 0 over zi is equal to 0.4, and it increases with stability, which reflects stronger turbulence. The covariance profiles are more variable, especially under weak instability that you can see here. So these are heat and humidity spectrograms. Trust me, they look a little strange. I am here to teach you how to interpret them. It took me a while to fully understand these plots as well. So before getting into that, understanding spectrograms. So this is a blank one. Z over Zi is on the x-axis, so that is increasing height. And then on the y-axis, this is increasing scale. So looking at normalized wavelength here. Now let's add this line here. So this is where the normalized wavelength is equal to 1. So that is a scale of the atmospheric boundary layer depth that we're seeing. Above that line, you have large scale motions. And so that means that the scales are larger than the ABL depth. And below you have small scale motions, which indicate that it is smaller than the smaller scales than the atmospheric boundary layer depth. So now let's take a look at the temperature spectrograms. So I have added that line in for you for each one of those plots. So starting with the left, here, this is highly unstable cases, and this is a composite mean for those cases. So temperature variance is broadly distributed across a wide range of scales and heights with significant energy at large and small scales, you can see there. So you can see it's closer to the bottom of the boundary layer. And then there's also around the scale of the boundary layer, around 1, there is some power that is occurring there. Next, looking at the middle plot, which is the moderately unstable cases. You can see that there are the strongest fluctuations near the surface with power dissipating with height there. So this vertical decay suggests that turbulent mixing is weaker aloft and that temperature variation is confined to the surface there. Finally, getting to our weakly unstable cases. On the right, you can see that they're concentrated at larger scales than the ABL depth, especially at lower and middle portions of the CBL there. So now that we've examined temperature, let's take a look at humidity. So obviously, it looks a lot different than temperature. It's a different story. So looking at the highly unstable cases here, again, let's add that line there. So right in here, there's broad spectral power with small scale humidity variance that's dominant in the lower to mid convective convective boundary layer. Moisture shows less vertical extent than temperature, which then suggests that there's stronger influence from surface sources. Next, looking at the middle plot here, you can see that there is spectral energy that's concentrated at smaller scales and lower heights. So it's lower than 0.4 there, which indicates that there's reduced mixing and weaker coherent structures that are occurring. Finally, looking at weakly unstable. So on the right, you can see that the spectral power is weakest and confined near the surface. And there is low heat flux and strong shear that limits that vertical mixing and moisture transport that is occurring. So now taking a look at future work. So the first thing that we'd like to do is continue looking at spectrograms and produce and analyze evaporative fraction there. You can see it is very trimodal, and we want to look at the dominant modes, which would be 0 to 0.3, we've got 0.3 to 0.7, as well as 0.7 to 1 there. The second thing we're interested in looking at is identifying and analyzing uniform temperature zones and uniform humidity zones to be able to understand their their structural properties. And then finally, normalize vertical flux profiles to improve collapse across cases in the spaghetti plots that I was showing you earlier, so we can get a better idea of what exactly is occurring within our cases. And that would be normalizing them with W star, Q star, as well as theta star. So now getting into our conclusions here. So when you have a higher evaporative fraction that is associated with weaker instability, you'll have a moist surface, and that increases the latent heat and suppresses buoyancy-driven turbulence. When you have a lower evaporative fraction here, it is associated with higher instability. And that's when you have more of a dry surface and the buoyancy production is enhanced. So now you have the sensible heat is increasing. So the instability strongly modulates vertical mixing and spectral energy distributions within the convective boundary layer. Looking at temperature for the highly unstable regimes, they support deeper and broader scale turbulent structures, which enhance vertical transport of that heat and moisture. Next, looking at moderately unstable cases, those regimes show confined variance near the surface, which indicate reduced mixing and weaker large scale coherence. Looking at weakly and unstable, these conditions suppress turbulence, which limit vertical transport and concentrate energy near the surface. And finally, looking at humidity, it is more constrained than temperature. Again, as I said earlier, it's a completely different story than what we see with heat. And it reflects stronger influence from surface sources, as well as weaker vertical mixing that is occurring. So before we end, I have some acknowledgements. So thank you to Dr. Salesky, as well as Dr. Brian Green and Dr. Madeline Frank for their invaluable mentorship and guidance and support within this project. I appreciate all of your assistance and help. And special thanks to Rob Newsome at the Pacific Northwest National Laboratory for his assistance with data selection and gathering. Also, this work is supported by the U.S. Department of Energy and their Atmospheric System Research Program. So here are my references. And do you all have any questions? I apologize for the technical issues.
I have a question about your data kind of exclusion methods. So I was really surprised to see that there was such a reduction in data coming from the research. Was your exclusion based on if there were hours missing that whole day by excluded?
No, so we look at, so 1 hour is equal to 1 case there. So the big reduction that we started with was getting rid of all nighttime cases. So all nighttime hours. Because again, we want to look right at the convective boundary layer. And then also getting rid of cloud cover. We originally looked at doing 3% or less. And that originally gave us enough cases. However, as we continued to filter them based on the other criteria here, that gave us less than 100. And we wanted to stay above that 100 mark. So we had enough cases to look at the different regimes. Did that answer your question? Okay.
There are no other questions. Thank you. And thanks for ready out last week. So I appreciate that. And good luck to all of the final week and sign up, literal finals. And thank you.
Yeah, and thank you guys for coming for the last seminar.